On January 24, 1961, a B-52 Stratofortress broke apart over North Carolina, dropping 2 nuclear bombs. One of them went through nearly its entire arming sequence. It wasn't enemy fire that caused it. It was structural failure, fuel imbalance, stress, and aerodynamic loads beyond what the airframe could tolerate. Now imagine that same aircraft, weighing over 220 tons at takeoff, being ordered into the air within minutes. Not hours. Not carefully staged. But an emergency scramble. From a physics standpoint, that shouldn't be easy. Because getting something that heavy airborne is not about heroism. It's about thrust-to-weight ratios, runway length, lift coefficients, and very unforgiving thermodynamics. And if any one of those variables is off, even slightly, the aircraft doesn't climb. It overruns the runway. Or worse. So today, we're going to break down what really happens when U.S. Air Force pilots and crew rush a B-52 for an emergency takeoff, not from a cinematic perspective, but from an engineering one. And why, according to the laws of physics, it's far more difficult than it looks. The B-52 was designed during the early Cold War to deliver nuclear weapons across continents. But here's the real constraint. Nuclear deterrence only works if your bombers survive long enough to launch. If they're destroyed on the ground, they're irrelevant. So the U.S. developed alert posture systems, aircraft fueled, armed, and ready to move within minutes. Visual, archival footage of Cold War B-52 alert ramps lined up nose to tail. During peak Cold War tension, B-52s sat on what was called chrome dome alert engines, sometimes prepped for immediate ignition. Why? Because the time between radar detection and impact from an incoming missile could be under 30 minutes. Subtract decision-making time. Subtract crew boarding. Subtract engine spool up. You might have 10 to 15 minutes left. For a 220-ton aircraft, that's not generous. Let's reduce this to first principles. An aircraft takes off when lift greater than or equal to weight. Lift is defined by the equation L equals 1/2 rho v superscript 2 SCL, where rho equals air density, v equals velocity, S equals wing area, CL equals coefficient of lift. The B-52 has an enormous wing, roughly 4,000 square feet. But its maximum takeoff weight exceeds 488,000 pounds. To generate enough lift, it must reach approximately 160 to 180 knots. That's around 200 miles per hour. And here's the constraint. Acceleration depends on thrust minus drag. The B-52 uses 8 turbofan engines producing a combined thrust of roughly 136,000 pounds. Visual, exploded view of turbofan engine airflow path. That sounds like a lot. But at full fuel load, its thrust-to-weight ratio is under 0.3. For comparison, modern fighter jets often exceed 1.0. Meaning they can climb vertically. The B-52 cannot. It must carefully accelerate down a long runway. In an emergency, that's terrifyingly unforgiving. Here's something rarely discussed. Jet engines are not instant-on devices. They are thermodynamic systems governed by compressor stall limits, turbine blade temperature limits, fuel-air mixture stability. When a scramble order is given, ground crews sprint to the aircraft. Visual, time-lapse recreation of crew laddering and engine ignition sequence. The pilots initiate start procedures for 8 engines. Each engine must Spin up using compressed air or auxiliary power. Reach idle RPM without flameout. Stabilize exhaust gas temperature. If you rush this process, you risk a hot start, overheating turbine blades made from nickel superalloys. Why does that matter? Because turbine blades operate near 1500 degrees Celsius. That's close to their material limits. Materials science here is critical. These blades use single crystal structures to prevent creep and stress fracture. Visual, microscopic structure of single crystal turbine blade. In an emergency scramble, engineers must balance speed with thermal safety. Too slow? You miss the launch window. Too fast? You destroy an engine. Real engineering is compromise. Let's quantify the takeoff roll. Acceleration is defined as A equals thrust minus drag minus rolling resistance / mass. At maximum load, the B-52 may require over 8,000 feet of runway. Now imagine that runway is wet. Air density changes with temperature. Hot day. Lower density. Lower density means less lift and less engine thrust. So you need even more speed. Which means more runway. Which means less margin. This is why emergency takeoff procedures include performance charts. They're not optional. They are survival math. Visual, performance chart overlay showing temperature versus required runway. The B-52's wings are long and narrow. High aspect ratio. Why? Because induced drag decreases as aspect ratio increases. That makes cruise flight efficient. But there's a trade-off. Long wings flex dramatically. Visual, slow motion footage of B-52 wing flex in turbulence. At takeoff, the wings can flex several meters upward. Why is that important? Because during rotation, the moment the nose lifts, the wing angle of attack increases. Too much too soon, and you risk boundary layer separation. Which means stall. And at 200 miles per hour, just meters above runway level, that's catastrophic. So pilots rotate gently. Even in an emergency. Physics does not care about urgency.